Welcome to Fuzzy Mathematics, the basics. In the previous lecture, we have talked about nest of sets. In this lecture, we are going to talk about the representation theorem, which is the main topic in this lecture. We will not give all of the theorem at once. Let U of x be the set of nests of sets in X. Let f of x be the fuzzy power set of X. Define T as follows. T of H is the union of the scalar multiplication of lambda and each of lambda. Lambda is in the closed interval from 0 to 1. First, we will show that T is a mapping from the set of nests of sets to the fuzzy power sets. Suppose H is a nest of sets. Let lambda be a real number in the closed interval from 0 to 1. Each of lambda be a crisp set. Then the scalar multiplication of lambda and each of lambda is a fuzzy set. And then T of H, which is the union of these scalar multiplications, is a fuzzy set. So T is an assignment of exactly one fuzzy set T of H to each nest of sets H. T is a surjection. Suppose A is a fuzzy set. Define H of lambda is the cut of A at level lambda. Lambda is in the closed interval from 0 to 1. If lambda 1 is less than lambda 2, then the cut of A at level lambda 2 is a subset of the cut of A at level lambda 1. So H is a nest of sets. By the resolution principle 1, we have the union of the scalar multiplication of lambda and its sublambda equals A. So T of H is the same as A. Therefore, the mapping T is a surjection. Next, we will prove that the strong cut of the fuzzy set T of H at level lambda is a subset of H of lambda, and H of lambda is a subset of the cut of T of H at level lambda for all lambda in the closed interval from 0 to 1. That is, H of lambda is in between the strong cut and the cut of the fuzzy set T of H at level lambda. First, we will prove that the strong cut of the fuzzy set T of H at level lambda is a subset of H of lambda. Suppose lambda equals 1. By the property of the strong cuts, we have the strong cut of T of H at level 1 is the empty set. So the strong cut of T of H at level 1 is a subset of H of lambda. Next, suppose lambda is in the interval from 0 to 1, excluding 1. If X is in the strong cut of T of H at level lambda, by the definition of strong cuts, we have the degree of membership of X in T of H is greater than lambda. By the definition of T of H, the degree of membership of X in the fuzzy set T of H equals the degree of membership of X in the union of these scalar multiplications. By the definition of union of fuzzy sets, the degree of membership of X in the union equals the supremum of the degrees of membership of X in these scalar multiplications. By the definition of scalar multiplication, we have the degree of membership of X in the scalar multiplication of alpha and H of alpha is the minimum of alpha and H of alpha of X. Because the supremum is greater than lambda, lambda is not upper bound of these numbers. So there exists alpha 0 in the closed interval from 0 to 1, such that the minimum of alpha 0 and H of alpha 0 of X is greater than lambda. And that means alpha 0 is greater than lambda. And H of alpha 0 of X is greater than lambda. Considering that H is a nest of sets, H of alpha 0 is a crisp set. So H of alpha 0 of X must be 1. That is, X is in H of alpha 0. Considering that alpha 0 is greater than lambda, together with H is a nest of sets. H of alpha 0 is a subset of H of lambda, so X is in H of lambda. Therefore, we have proved that the strong cut of the fuzzy set T of H at level lambda is a subset of H of lambda. Next, we will prove that H of lambda is a subset of the cut of T of H at level lambda. Suppose lambda equals 0. By the property of the cuts, the cut of T of H at level 0 is the universal set. So H of 0 is a subset of the cut of T of H at level 0. Next, suppose lambda is in the interval from 0 to 1, excluding 0. If X is in H of lambda, then H of lambda of X equals 1. By the definition of T of H, the degree of membership of X in T of H equals the degree of membership of X in the union of the scalar multiplications. By the definition of union, the degree of membership of X in the union equals the supremum of the degrees of membership of X in these scalar multiplications. And by the definition of scalar multiplication, the degree of membership of X in the scalar multiplication of alpha and H of alpha is the minimum of alpha and H of alpha of X, considering that the supremum is taken over all the alpha in the closed interval from 0 to 1. It is greater than or equal to the minimum of lambda and H of lambda of X. And we have shown that H of lambda of X equal to 1. So the minimum of lambda and 1 is lambda. The degree of membership of X in the fuzzy set T of H is greater than or equal to lambda. That means X is in the cut of T of H at level lambda. Therefore, we have proved that H of lambda is a subset of the cut of T of H at level lambda. Now we have shown that T of H is a fuzzy set, and H of lambda is between the strong cut and the cut of the fuzzy set T of H at level lambda for all lambda in the closed interval from 0 to 1. By resolution principle 3, we have if lambda is in the interval from 0 to 1, excluding 0, then the cut of T of H at level lambda is the intersection of H of alpha, alpha less than lambda. And if lambda is in the interval from 0 to 1, excluding 1, then the strong cut of T of H at level lambda is the union of H of alpha, alpha greater than lambda. The conclusions here will be used in the latter part of the proof. Next, we will prove that the mapping T is a homomorphic mapping. A homomorphic mapping is a mapping of a set onto another set or itself in such a way that the result obtained by applying the operations to elements of the first set is mapped onto the result obtained by applying the corresponding operations to their respective images in the second set. In short, a homomorphic mapping is a mapping which preserves operations. Let H be a nest of sets. Let I be the identifier set. In order to show that the mapping T is a homomorphic mapping, we need to show that T satisfies the following properties. Firstly, T of the union of Hi equals the union of T of Hi. Secondly, T of the intersection of Hi equals the intersection of T of Hi. Thirdly, T of the complement of H equals the complement of T of H. We will prove the first equality by showing that the strong cuts of the two fuzzy sets at the same level are equal. It is easy to see that if lambda equals 1, then the strong cut of each side is the empty set. Now suppose lambda is in the interval from 0 to 1, excluding 1. By the above discussion, the strong cut of T of H at level lambda equals the union of H of alpha, alpha greater than lambda. Replace the H with the union of HI. Then we have the strong cut of T of the union of HI at level lambda equals the union of HI of alpha, alpha greater than lambda. By the definition of union of nests, the union of HI of alpha equals the union of HI of alpha. Here, the union is taken twice, first for all I, then for alpha greater than lambda. So we can change the order of taking the unions. That is, first for all alpha greater than lambda, then for all I. So it is going to be the union of HI of alpha, alpha greater than lambda, then for all I. Again, by the above discussion, replace H with HI, then we have the union of HI of alpha, alpha greater than lambda, equals the strong cut of T of HI at level lambda. By the properties of the strong cuts, we can change the order of taking the strong cut and taking the union. So it is going to be the strong cut of the union of T of HI at level lambda. Now we have shown that the strong cuts of the two fuzzy sets at the same level are equal for all lambda in the closed interval from 0 to 1. By resolution principles 2, we have the two fuzzy sets are equal. Similarly, we can prove the other two equalities. Therefore, T is a homomorphic mapping. Now we can give the representation theorem. Let T be a mapping from the set of nests of sets to the fuzzy power set, which assigns exactly one fuzzy set to each nest of sets. T of H is the union of the scalar multiplication of lambda and H of lambda. Then T is a surjection, and it is a homomorphic mapping. And the following properties hold. Firstly, H of lambda is in between the strong cut and cut of the fuzzy set of T of H at level lambda for all lambda in the closed interval from 0 to 1. Secondly, if lambda is in the interval from 0 to 1 excluding 0, then the cut of the fuzzy set T of H at level lambda equals the intersection of H of alpha, alpha less than lambda. Lastly, if lambda is in the interval from 0 to 1, excluding 1, then the strong cut of the fuzzy set T of H at level lambda equals the union of H of alpha, alpha greater than lambda. That's the representation theorem. Next time, we will continue this topic. Thank you.